Welcome to the Deep Dive. Today, we're really getting into the weeds of material science and engineering.
Yeah, it sounds maybe a bit dry, but it's actually fascinating stuff.
It really is. Think about it.
Yeah.
I mean, everything around us, everything tangible is made of something. And understanding why those somethings act the way they do, well, that's kind of fundamental to building pretty much anything.
Absolutely. And we've got some great source material to work with here. It really unpacks the nuts and bolts.
So we're looking at the basic building blocks first, atoms and how they stick together.
Exactly. Starting there and then zooming out to see how the different families of materials, metals, ceramics, polymers, even composites get their unique characteristics.
Right, like why one is strong and another is stretchy.
And how they behave under different conditions, different stresses, temperatures, all that.
And the range in our sources is pretty wild, isn't it? We're talking about the sheer strength of steel alloys.
Yep.
But also, like, the incredible flexibility of some polymers. And even diving into why things break.
Oh yeah, failure mechanisms, what happens inside materials when things heat up, electrical properties, magnetic properties. It's a lot.
But it sounds more exciting than maybe the textbook version.
That's the plan. We want to pull out the core ideas, those aha moments, and the practical side of it.
Without drowning in jargon.
Exactly. Keep the technical talk manageable. The goal is really to give everyone listening a solid foundation, help understand why the materials in our lives are the way they are.
Okay, sounds great. So this huge world of materials, where do we even start trying to organize it?
A really good first step is classification. We can basically lump solid materials into three main categories: metals, ceramics, and polymers.
Okay, the big three.
Yeah, and each group has its own, let's say, signature chemical structure.
Metals first, then. And I think metal, shiny, conducts electricity, conducts heat. What's going on underneath?
The key is something called metallic bonding. It's a bit unusual. Imagine the outer electrons, the valence electrons of the metal atoms. They aren't really tied to just one atom. They're more like shared in this sort of communal sea of electrons that flows around the positive ions.
A sea of electrons. I like that.
And it's that freedom, that easy movement of electrons that lets metals like steel, aluminum, copper conduct electricity and heat so well. It's like a highway for them.
That makes sense. Okay, so then ceramics. They feel like the total opposite. Often hard, maybe brittle insulators?
Yeah, typically. Ceramics are usually the compounds made between metallic and non-metallic elements.
Like metal oxides or carbides.
Exactly. Things like aluminum oxide, silicon carbide, even glass. And their bonds are generally different, ionic or covalent.
Ionic and covalent, remind me quickly.
Ionic is like a give and take of electrons, creating positive and negative ions that attract strongly. Covalent is more about sharing electrons between specific atoms.
Okay.
And these bonds are usually very strong and directional. They lock the atoms rigidly in place.
Which explains the hardness and high melting points.
Precisely. That rigidity makes them hard. Compare that to the looser electron sea in metals. It's a very different setup.
Right. And polymers. That feels like a whole other world.
Right.
Rubber bands, plastics. Very versatile.
Polymers are fascinating. They're often organic, based on carbon, forming these huge, long-chain molecules, repeating units linked together.
Like polyethylene, PVC.
Yep, those are common ones. Nylon, too. Because these chains are so long and sometimes only loosely connected to each other, polymers tend to be less dense. They're often not as stiff or strong as metals or ceramics, but they can be incredibly flexible or lightweight. Big advantages there.
Okay, so metals, ceramics, polymers. What about composites? That sounds like a mix and match.
That's basically it. Composites are engineered materials made from two or more of those primary types.
To get the best of both worlds.
Or even properties that neither starting material has on its own. Think carbon fiber reinforced polymer. You mix strong carbon fibers into a polymer matrix.
Right, for aerospace or race cars.
Exactly. You get incredible strength, but keep it really light. It's like creating a material superhero team.
Our sources give us some visuals for comparing these two, right? Figures.
Yes. Figure 1.5 is quite revealing. It shows tensile strength, basically, how much pull a material can take before it breaks.
Right.
And it uses a logarithmic scale, which is important because the differences are huge.
What jumps out?
Well, you see some steel alloys way up high, handling stresses maybe thousands of times greater than, say, common plastics.
Wow.
It really hammers home why you don't build bridges out of, Tupperware.
Makes sense. And it's not just about ultimate strength, but also resisting cracks.
Right, that's fracture toughness. Figure 1.6 shows that, again on a log scale.
And how do they stack up there?
Metals generally do very well. High resistance to cracks growing, that's why you can bend a paperclip a few times.
Oh, okay.
Ceramics, though, tend to have low fracture toughness. They can shatter more easily if there's a flaw. Polymers and composites, they show a wider range depending on the specific material.
So choosing the right material is really about matching these properties to the job. Okay, let's go deeper. Down to the atoms themselves. Basic structure.
Okay, so every atom has a nucleus, protons, neutrons with electrons orbiting around it.
In shells.
Right, and specific energy levels or shells, and even subshells within those. Table 2.1 lays out how many electrons fit in each.
Gotcha.
But the real action for bonding involves the outermost electrons, the valence electrons.
They're the ones that interact.
Yeah, think of them as the atom's hands reaching out to connect with other atoms.
And these connections, these bonds, that's what holds materials together. What are the main types?
There are three main primary bonds, strong ones: ionic, covalent, and metallic, which we mentioned, and then weaker secondary bonds.
Ionic first.
Ionic bonding is basically electrostatic attraction. Think magnets.
Opposites attract.
Exactly. One atom might effectively donate an electron to another, creating a positive ion and a negative ion. Then, zap, they stick together.
Like table salt, NaCl.
Perfect example. Or magnesium oxide, MgO. Table 2.3 shows these tend to have high bonding energy as strong attractions, which leads to high melting temperatures. It takes a lot of energy to break them apart.
Okay, strong electrical grip. Covalent.
Covalent is more like sharing. Atoms share pairs of valence electrons to get a more stable arrangement.
Like in silicon. Or diamond.
Precisely. These shared pairs create strong directional bonds. Again, generally high bonding energies, high melting points, like atoms holding hands really tight.
And metallic bonds. Back to the electron C.
Back to the C. The valence electrons are delocalized, shared among all the atoms in the metal.
Which allows conductivity.
Right. That free flow is key. Metals like aluminum, iron, tungsten have this. And interestingly, the strength can vary quite a bit. So melting points for metals cover a wider range.
You also mentioned weaker secondary bonds.
Yeah, these are much weaker than primary bonds. Van der Waals forces, hydrogen bonds.
What causes them?
They arise from subtle fluctuations in electron distributions, creating temporary or small permanent dipoles, slight positive or negative ends on molecules that attract each other weakly.
So they're important for?
Things like noble gases when they liquefy, like argon, or molecules like chlorine, ammonia, even water. Table 2.3 shows these have much lower melting points because these weaker attractions are easier to overcome. Think of it like a gentle nudge versus a firm handshake.
So the bond type and strength really set the stage for everything else. Is there a way to visualize this bond strength?
There is. We use bonding energy curves. Imagine plotting the potential energy between two atoms as you vary the distance between them.
Okay.
There's an ideal distance and equilibrium spacing where the energy is lowest. That's the most stable spot.
If you push them closer or pull them apart.
The energy goes up. You have repulsive forces if they get too close, attractive forces if they're pulled apart. Equation 2.11 describes this mathematically. The deeper that energy well at the minimum point, the stronger the bond.
Got it. So atoms link up. How does this translate to the bigger picture? The structure of solids.
That takes us into the structure of crystalline solids. In crystalline materials, atoms aren't just randomly jumbled. They arrange themselves in very orderly, repeating 3D patterns. A crystal lattice.
Like stacking bricks neatly.
Exactly. As opposed to non-crystalline or amorphous materials like glass or some polymers where the arrangement is more random, like a pile of sand.
So crystals have this internal order. What are the common patterns, especially in metals?
Two really common ones are face-centered cubic, or FCC, and body-centered cubic, BCC.
FCC first.
Okay, FCC. Think of a cube. You have an atom at each corner plus one atom right in the middle of each face. Metals like aluminum, copper, gold have this structure.
And it's efficient packing.
Very efficient. Each atom has 12 nearest neighbors. That's its coordination number. And the atomic packing factor, or APF, is 0.74, meaning 74% of the volume is filled by atoms. It's like the densest way you can stack spheres.
Okay. And BCC, body-centered.
Still a cube with atoms at the corners, but instead of face atoms, there's one single atom right in the very center of the cube.
Like iron at room temperature.
Yep, that's a key example. Chromium, tungsten 2. Its coordination number is lower, just 8, and it's slightly less efficiently packed, with an APF of 0.68.
Then there's also hexagonal close-packed, HCP.
Right. found in metals like magnesium, titanium, zinc. Cadmium table 3.1 lists them. HCP is actually just as efficient at packing as FCC.
Same coordination number and APF.
12.74. It's just a different stacking sequence of those close packed layers. Gives it hexagonal symmetry instead of cubic.
Our sources mention a simple cubic structure too, figure 3.23.
Yeah, simple cubic is just atoms at the corners of a cube. It's actually quite rare for metals because it's not very efficiently packed. APF is only 0.52. Polonium is one example.
So these repeating unit cells build up the crystal. How do we talk about specific spots or directions inside that structure?
We use specific notation, crystallographic points, directions, and planes. We need a precise way to describe locations and orientations.
Miller indices.
Miller indices, in parentheses like HHKL, are used for planes. They're based on how a plane intercepts the crystal axis, square brackets, UW, denote directions.
So it's like a coordinate system for the atomic arrangement.
Pretty much. Figure 3.7 shows the special coordinate system used for hexagonal cells, and figure 3.8 gives examples of how directions and planes are labeled. It's a universal language for crystallographers.
Seems very precise. What about how densely atoms are packed along a line or on a plane?
That's linear density and planar density. Linear density is atoms per unit length along a direction. Planar density is atoms per unit area on a plane.
And why are those important?
They become really important when we talk about how materials deform plastically. Specifically for slip systems, which we'll get to. It relates to how easily layers of atoms can slide past each other.
Slip systems. Sounds like the mechanism for bending metals.
Exactly. The planes and directions with the highest densities are typically the easiest paths for atoms to slip along, like cards sliding more easily on their flat faces.
Okay, makes sense. How do we even know these structures exist? Our sources mention X-ray diffraction.
XRD is a cornerstone technique. You shoot X-rays at a crystalline material, and the X-rays diffract or bounce off the regularly spaced planes of atoms according to a specific rule called Bragg's Law Equation 3.16, relates the angle, wavelength, and plane spacing.
So you measure the diffracted beams.
And from the angles and intensities, you can work backward to figure out the spacing between atomic planes and deduce the entire crystal structure. It's like using echoes to map the internal architecture.
Clever. So is a real chunk of metal usually one perfect crystal?
Rarely. Perfect single crystals exist, but they're usually grown specifically. Most engineering materials are polycrystalline, meaning they're composed of many tiny individual crystals or grains packed together. Each grain is typically oriented differently from its neighbors.
And the boundaries between these grains are important.
It's very important. They're called grain boundaries, shown nicely in figure 4.10. They influence properties significantly. And also, properties can depend on direction, especially in single crystals or textured polycrystals. That's anisotropy.
Like wood grain. Easier to split along the grain.
That's a great analogy for anisotropy, yes.
It's all starting to link up. Atomic bonds lead to crystal structures, which influence the overall behavior. But you mentioned these structures aren't perfect. Defects.
Absolutely. Real crystals always contain imperfections or defects. We can group them. Point defects, line defects, and area defects.
Point defects you are.
Small scale.
Yeah.
Like a missing atom of vacancy. Or an extra atom squeezed in where it doesn't belong, an interstitial atom.
Okay, line defect.
These are one-dimensional defects, and the most important type is the dislocation. It's like an extra half plane of atoms inserted into the lattice, causing a distortion along a line.
And area defects.
Those are two-dimensional, like the external surface of the material itself, or those grain boundaries we just talked about, the interfaces between different crystal grains.
Dislocations sound key. You mentioned slip earlier. How do they relate to deformation?
Dislocations are fundamental to plastic deformation in crystalline materials, especially metals. Chapter 7 and figure 7.1 show this really well.
Ow.
Instead of breaking all the bonds across a plane simultaneously, which would take huge force, a dislocation allows slip to happen sequentially. The dislocation line moves through the crystal, breaking and reforming bonds row by row.
Like an inchworm moving.
That's a perfect analogy. It allows planes of atoms to slide over each other at much lower stresses than if the crystal were perfect. Without dislocations, metals would be incredibly strong, but also very brittle.
So their movement is what gives metals ductility.
Largely, yes. The ease of dislocation motion dictates how easily a metal can deform plastically.
And this happens on specific planes and directions? the slip systems.
Exactly. A slip system is the combination of a slip plane, usually the most densely packed plane, and a slip direction, usually the most densely packed direction within that plane. That's the path of least resistance for dislocation movement.
So these imperfections aren't always bad news. Sometimes we use them to our advantage.
Definitely. We deliberately manipulate defects to make materials stronger. These are strengthening mechanisms.
That's how they work.
They generally work by making it harder for dislocations to move. For instance, grain size reduction. More grain boundaries mean more obstacles for dislocation.
Okay.
Solid solution strengthening. Adding impurity atoms distorts the lattice locally, creating speed bumps for dislocations. And strain hardening, or cold working, like bending that paperclip, increases the density of dislocations. They get tangled up and impede each other's motion, like a traffic jam.
So we intentionally create more roadblocks for these dislocations. What if you heat up a metal that's been cold worked? Does it soften again?
I can, yes. Heating allows atoms to move around more easily, diffusion. This can lead to recovery where some internal stresses are relieved.
And then?
With enough heat, you get recrystallization. New strain-free grains start to form and grow, replacing the deformed structure. Figure 7.21 shows this.
Wiping the slate clean, basically.
In a way, yes. And if you hold it at temperature longer, these new grains can grow larger. That's grain growth. These processes generally decrease strength but increase ductility. It's called annealing.
Okay, structure, defects, strengthening. Now let's get practical. How do materials actually respond when we apply forces? Mechanical properties.
Right. When you apply a force, the material experiences stress that's force per unit area. And it deforms, which we measure as strain, the change in dimension relative to the original.
And we can pull, push, twist.
Yep. Figure 6.1 shows tension, pulling, compression, pushing, shear, sliding, torsion, twisting. The relationship between stress and strain is key.
Like how stiff it is or how much it stretches before breaking.
Exactly. First, there's elastic deformation. If you remove the load, it springs back. Non-permanent.
Like a rubber band initially.
Sort of. The slope of the stress-strain curve in this elastic region is Young's modulus, E. It measures stiffness. Higher E means stiffer material. There's also a shear modulus, G, for shear stress, and Poisson's ratio, which describes how it bulges or contracts sideways when stretched or compressed. Oh, and sometimes a tiny bit of time-dependent elastic strain called anelasticity.
But if you pull harder, eventually it stays deformed. Plasticity.
Yes. Once you pass the elastic limit, you get plastic deformation, permanent change. The stress at which this starts is the yield strength.
A critical value for engineers.
Absolutely. If you keep increasing the stress, you eventually reach the tensile strength, the maximum stress the material can handle, before it starts to neck down and fail.
What about how much it can deform before breaking? Ductility.
Right. Ductility measures that ability to deform plastically, often expressed as percent elongation or percent reduction in area at fracture. Problem 6.3 deals with calculating these.
So ductile means it stretches a lot before snapping.
Yes. Toughness is related but slightly different. It's the total energy a material absorbs before fracture. It combines strength and ductility. A tough material resists both high stress and significant deformation.
We also hear about hardness testing. How does that fit in?
Hardness measures resistance to localized plastic deformation, like scratching or denting. Tests like Rockwell and Brunel in Table 6.6 press a standardized indenter into the surface.
And harder usually means stronger.
Generally, there's a good correlation between hardness and tensile strength. It's a relatively easy test to perform.
So these tests give us numbers to compare materials. But what about when they actually fail? Fracture.
Failure can happen broadly in two ways: brittle or ductile fracture. Figure 8.1 shows the difference clearly.
Brittle is.
Sudden failure with little or no warning, little plastic deformation. The crack moves fast. Think snapping chalk. Fracture surface often looks relatively flat and crystalline.
And ductile.
Involves significant plastic deformation for stretching, necking down. The crack grows more slowly. Think tearing taffy. The fracture surface looks rougher, more fibrous.
Can we predict when a crack might cause failure even if it's small? Fracture mechanics.
Yes. Fracture mechanics gives us tools for that. It introduces fracture toughness, often KIC, from equation 8.6.
What does that measure?
It measures a material's resistance to crack propagation when a flaw is already present. It considers the applied stress and the size of existing cracks or defects, like those shown in figure 8.9. High fracture toughness means it can tolerate larger flaws.
Super important for safety. What about failures over time? repeated stress, or high temperatures.
That brings us to fatigue and creep. Fatigue is failure under cyclic loading repeated stress cycles, even if the stress is below the yield strength.
Like bending a wire back and forth until it snaps.
Exactly. SN curves, like in figure 8.9, plot stress amplitude versus the number of cycles to failure. Some materials show a fatigue limit, a stress below which they can supposedly endure infinite cycles.
But things like scratches can make it worse.
Hugely. Surface condition, sharp corners, stress concentrations, corrosive environments, all can drastically reduce fatigue life.
In creep.
Creep is slow, continuous deformation over time under a constant load, especially at high temperatures. Think of a lead pipe slowly sagging under its own weight over years.
Okay, these long-term effects are crucial for design. Let's switch gears now. How does structure change with temperature or mixing elements? Phase diagrams.
Phase diagrams. They're like maps for material scientists. They show which phases are stable under different conditions, temperature, pressure, composition.
Phases being?
Uniform parts of a system with distinct characteristics. Like ice, liquid water, and steam are 3 phases of H2O.
So we define the components, the pure substances involved, and the system, which is the range of compositions we're looking at.
Right, and concepts like solubility limit how much of one thing dissolves in another, like sugar and water.
Even single substances have phase diagrams.
Oh yes. Figure 9.2 shows the one for water pressure versus temperature, showing the solid, liquid, and vapor regions and the lines where they coexist.
But for alloys, mixtures of metals, we use binary phase diagrams, 2 components.
That's where they become really powerful for understanding alloys. They map phases versus temperature and composition.
Like copper nickel.
Yeah.
Figure 9.3.
Yeah, Cunei is a simple one. They mix completely in both liquid and solid states. Others are more complex, like copper silver, figure 9.7, or lead tin, figure 9.8.
What makes them complex?
Things like eutectic reactions. That's where a liquid phase cools and transforms directly into 2 different solid phases simultaneously at a specific temperature and composition.
Like a specific mixture freezing out all at once.
Exactly. Lead tin solder relies on this.
These diagrams have lots of lines and regions. How do we read them?
You pick a temperature and overall composition. The diagram tells you which phase or phases are stable there.
And if it's 2 phases?
In a 2-phase region, you draw a horizontal tie line at your temperature. Where it hits the phase boundaries tells you the exact composition of each phase.
Okay. And how much of each phase?
That's where the lever rule comes in. Equations 9.1b and 9.2b. It's like balancing weights on the tie line. It lets you calculate the weight fraction of each phase present.
Clever analogy. You mentioned eutectic, liquid to 2 solids. Are there solid to solid transformations too?
Yes, eutectoid reactions. Similar idea, but one solid phase transforms into 2 different solid phases upon cooling.
And this is super important for steel, right? The iron-carbon diagram.
Absolutely critical. Figure 9.24, the iron-iron carbide Fe3C diagram, is the bedrock of steel heat treatment.
What's the key feature there?
It has a crucial eutectoid reaction at 0.76 weight percent carbon and 727 degrees Celsius.
What happens there?
A solid phase called austenite transforms upon cooling into 2 other solids. Ferrite, almost pure iron, and cementite, iron carbide Fe3C.
And that mixture has a name.
Yes, the layered microstructure formed is called pearlite. The diagram also helps classify steel's hypoeutectoid, less carbon, or hypereutectoid, more carbon, and predicts which phase forms first on cooling before the pearlite.
So controlling cooling through these transformations lets us tailor steel's properties, which leads us nicely into phase transformations themselves.
Exactly. These changes don't happen instantly. They involve 2 steps, nucleation and growth.
Nucleation is starting the new phase.
Right. Forming tiny stable seeds or nuclei of the new phase. This can happen randomly within the old phase, homogeneous, or more commonly start at existing defects or interfaces, heterogeneous.
And then growth.
The nuclei just get bigger until the transformation is complete.
And the speed, the rate of transformation matters.
Hugely. It depends strongly on temperature, as figure 10.8 shows. Usually slow at very high temps, low driving force, and very low temps, slow atom movement, diffusion. Fastest somewhere in between.
Which leads to those C-shaped curves on TTT diagrams.
Precisely. Time temperature transformation diagrams map out how long it takes for transformations to start and finish at different constant temperatures. They're like recipe books for heat treaters.
So you can dial in a microstructure.
Pretty much. Cool austenite slowly through the eutectoid point, you get coarse pearlite, relatively soft. Cool faster, you get fine perlite harder, stronger.
And even faster cooling.
You might form bainite, another microstructure, or if you cool extremely rapidly, quench it, you can bypass perlite and bainite formation altogether and form martensite.
Martensite. That's
Oh.
the really hard one.
Very hard, but also very brittle. It forms by a different mechanism, diffusionless or a thermal. The atoms shear into a new structure without needing to diffuse long distances.
So you often have to treat it afterward.
Yes. Martensite is usually tempered, reheated to a moderate temperature to increase its toughness and ductility, although this sacrifices some hardness.
And CCT diagrams.
Yeah.
Gin point 40.
Continuous cooling transformation diagrams, maybe even more practical, as they show what happens during continuous cooling, not just holding at one temperature, which is more common industrially.
Amazing control. Okay, wrapping up, our sources touch on material selection and design.
Yeah, choosing the right material is obviously critical in engineering. You have to weigh all these properties: strength, stiffness, toughness, fatigue life, corrosion resistance.
Depending on the application.
Exactly. Designing for fatigue means keeping stresses low, avoiding sharp corners, and economics always plays a role: cost, availability. Plus, nowadays, huge emphasis on sustainability, recyclability. Chapter 23 covers that and environmental impact.
Any specific examples?
Section 22.10 gives a great case study: materials for artificial hip joints. Talk about demanding requirements: biocompatibility, wear resistance, strength, fatigue life, all in one package.
Wow. It really pulls everything together. It's amazing how these deep atomic level ideas connect directly to building the world around us.
It truly is. Understanding that basic structure, the bonding, the classifications, how structure controls properties, and how we can manipulate it through processing, it's a really powerful lens.
So for everyone listening, maybe a final thought. As you go about your day, look at everyday objects, your phone, a chair, a bridge. Ask yourself, why this material? What properties were probably prioritized? And try to trace it back, even vaguely, to the atomic structures and processing we talked about.
It's a great exercise, puts it all into context.
Definitely makes you see the world a bit differently.
Absolutely. And remember, we've really just scratched the surface today. Material science is a huge dynamic field. If anything sparked your interest, there's always more to explore.
Fantastic. Well, thanks for taking this deep dive with us.
My pleasure.
Until next time, keep questioning and keep learning.